All the neural networks we've considered up to now have been densely connected, meaning we can think of each layer as having a vector of activations, and each neuron in one layer is connected to every neuron in the next. And dense networks are a great place to start because they are, in a sense, the most general neural networks. But it turns out that a lot of the time we can choose some other neural network architecture that is more effective for a particular application. And so starting with this video, we'll move away from dense architectures. And the first alternative architecture we'll consider is based on convolutional layers. Convolutional networks are particularly well adapted for image processing tasks. So far, when our inputs have been images, we have taken the pixels of the image and put them into one great big vector to serve as the input layer for our dense networks. But when we connect every neuron in our first hidden layer to every pixel of the image, that loses a lot of spatial information about which pixels are near one another. That seems like it would be helpful in processing that image. In principle, our dense network might well learn which pixels are near each other along the way, but if instead we use an architecture that actually captures spatial proximity of the pixels, that could give our network a big head start in learning to do image processing. And so the idea of a convolutional network is that we will connect our neurons to only the pixels from a small region of the image. If we have a neuron that only gets inputs from a small subregion of the image, then whatever that neuron learns to compute as we perform gradient descent and update its weights will be necessarily a function of that portion of the image. And then we can slide this input window and for other regions of the image have other sets of neurons. Then, just like in our dense layers, we had many neurons that were all receiving the same inputs, we can, for any given window of connections, have many different neurons that are processing that same subregion. This is important because each individual neuron can only learn a relatively simple function, and there might be many different types of processing we would want to do on a given spatial region. On top of spatial connectivity, the other key idea that gives convolutional layers a big head start is that we often want to apply the same function to many different regions of the image. For example, if one of these neurons learned to be an edge detection function, it would be really great to use that function all over the input image. We can't directly control what function a given neuron will learn, but it turns out that we can apply the same function all over the image. And we do this using weight tying. Our goal here is to ensure that for each region in the image, the first neuron is computing the same function, and the second neuron is computing the same function on each region, but the first and second neurons will be computing different functions from each other. To ensure that these two neurons compute the same function on two different regions of the image, we start by initializing the weights to be the same from each input in the previous layer. That means that the top left input to the red neuron will have the same initial weight as the top left input to the blue neuron. And likewise, both neurons will have the same initial weight from each other input pixel. And we also initialize them to have the same bias. We'll still generate the weights and biases randomly, but we'll do that once for each distinct neuron, and we'll copy the weights for the first neuron to the first neuron of every region in the image. Then when we are computing gradients and updating the weights, we will think of these weights that I've drawn in the same color as being a single parameter. And the contribution of this green weight to the overall loss of the network will be the sum of its contribution by all of the different paths, meaning we will sum up its contribution to each of the neurons that it's connected to. And that means we'll perform the same weight update for the green weight across every single neuron in the entire layer. So if two neurons started with identical weights and we perform identical updates, we know that they'll always be computing identical functions on their different subregions of the image. So the combination of local connectivity and weight tying lets the network learn to apply the same function to many different regions of the image, and we can give it many neurons to let it compute many different local functions, and all of this gives a big head start on learning to process images relative to the completely unstructured learning that we would do with a dense network. But now, if we use convolutional layers, we have a bunch of new hyperparameters that we have to think about. The first is we need to choose how big of a subregion each neuron will get its input from. And this is known as the kernel size. These kernels are most often square, and it's more common to choose an odd size, but neither of those is a strict requirement. And even if we choose odd size square kernels, we have a lot of options for how big that square should be. But also, when we are sliding our window of inputs, we don't necessarily have to slide it by the size of that window. Think back to our supposition that one neuron might learn to be an edge detector. If there were an edge right on the boundary of these kernels, then we might not be able to detect it. And so we might want to slide the window by less than the width of the kernel. And so we have a hyperparameter for the amount that we slide the window in each dimension. Here I've drawn in red an initial 4x4 kernel, and the blue kernel is offset by a stride of 1. Shifting by 1 gives the maximum possible overlap and ensures that we won't miss anything, but it also results in a very large number of neurons in our convolutional layer, and so we might sometimes prefer to shift by more and only have a small amount of overlap, like here, where relative to the red kernel, the green one is shifted by a stride of 3. Again, we could in principle choose different strides for the different dimensions of the image, but we usually don't. And we almost always want to choose the strides to be less than or equal to the kernel size so that we don't miss any inputs. We also said we want many neurons to be applied to each window of the image because each neuron computes a simple function, and we might need to compose many simple functions to do good image processing. And so that number of functions that we apply to the same region has several different names. Sometimes you'll see it called the output channels of the layer, or sometimes it's called the number of filters. And in this case, I've drawn 6 neurons all getting their inputs from this 4x4 region. But just like with dense networks, where we often use many more neurons in practice than it's practical to draw on the whiteboard, we'll often have many more channels or filters than what I have drawn here. There are also many other hyperparameters associated with convolutional layers, and I'm not enumerating all of the possibilities here. But another important one is what to do when we get to the edges of the image. It could often be the case that the combination of kernel size and strides that we've chosen doesn't perfectly match up with the dimensions of the input image, and so we might end up with some kernels that hang off the edge of the image, and in that case we need to decide what to do with the inputs that are out of bounds. And so we have a couple of hyperparameters associated with this padding. First is the amount, which has to do with how far off the edge of the image are we willing to go. Sometimes the amount of padding is forced by the relationship between the input size and the other parameters. But it turns out there are cases where it makes sense to deliberately let the kernels go further off the edge than they need to, which mostly have to do with preserving shape from one layer to the next in contexts that we'll talk about later. But regardless of how much padding we have, we also have to decide what values to put there, and the most common choices are to either fill in zeros or to duplicate the pixels near the boundary. And these are referred to as zero padding or same padding. Another hyperparameter that's often associated with convolution is an amount of pooling. And the purpose of pooling is to reduce the size of a layer so that we don't have an explosion in the number of parameters when we use multiple convolutional layers. So before getting into pooling, we should think about how many parameters we have in a convolutional layer, which means we need to talk about tensors. From a computer science perspective, a tensor is simply a multi-dimensional array. We can think of a vector as a one-dimensional array, or a matrix as a two-dimensional array. And so a tensor is just a generalization to an array of arbitrary dimensions. And if we think about the inputs when we do image processing and are not flattening them out into a vector, well, images have a height and a width, but it turns out they also have a third dimension because for every pixel in the image, there are 3 color channels for red, green, and blue. And so when we're working with 2D images and thinking about two-dimensional convolution, it turns out that our data is often represented with a 3-dimensional tensor. So supposing that our input image is 200 pixels high and 300 pixels wide, then the array storing each image is 200 by 300 by 3. But as we know, neural networks don't operate on just one data point at a time. Instead, they work with a batch of data. And so we might have yet another dimension that stores many different images. And so if we have 100 images in a batch, our tensor storing such a batch might have shape 200 by 300 by 3 by 100. But just like how with a dense network we don't typically draw the batch dimension, I will not try to draw the 4th dimension representing the batches here. But now let's think about what type of array stores the activations for a hidden convolutional layer. Well, since we are sliding our windows across a two-dimensional image, we can think of the first neuron of each window as being arranged in a two-dimensional grid. But then we also have several neurons that apply to each window, and so those stack up in a third dimension. And thus we can think of the hidden layer as having height and width dimensions corresponding to height and width from the image, reduced by some factor based on how quickly we slid the windows. And then the depth of the layer is based on how many functions we had per window. And so if our strides moved the window by 5 pixels each time, and we reduced the height and the width by a factor of 5, then we'd end up with 40 by 50 as the height and width of our hidden layer. But if we had 50 functions applying to each window, then we would have a depth of 50. And again, we have a fourth dimension for the batch size of 100 that I can't draw on the whiteboard. So this gives us a shape for the activation tensor, but how many neurons and how many parameters does that mean? So if we have 50 neurons per window and 40 by 60 windows, that gives us our number of neurons. So this layer would contain 120,000 neurons, but luckily a lot of those neurons share weights and biases. So in calculating the number of distinct parameters, we can completely ignore the height and width dimensions because we know the neurons are just duplicated over all of the different windows. So with 50 different functions, we end up with 50 biases, and 50 times the number of weights per function, total weights. And since we have 9 by 9 kernels, we will have 9 by 9 pixels coming into each neuron. And each pixel actually consists of 3 values for the 3 color channels. So we have 9 times 9 times 3 weights per neuron for a total of about 12,000 weights. So far, this is actually far fewer parameters than we would have with a dense network. Supposing that we had 50 nodes in a dense layer, which of note would be far less capable than this convolutional layer with 50 functions per window, then we would have 200 by 300 weights for each of those neurons times 50 neurons, giving us a total of 3 million parameters. And this is a big part of why it can be so much easier to train a convolutional network than a densely connected one. Unfortunately, the trouble comes when we try to add additional layers after this first convolutional layer. We might want to add additional convolutional layers that would have a sliding window over the 40 by 60 dimension of our hidden layer, which we could think of as aggregating together the functions computed on these small windows into new functions that are now applying to large regions of the image. Or at some point we could flatten out our tensor and have a densely connected layer that lets us make a prediction with a one-hot output vector. But either way, we'll end up with weights coming from each of the neurons in the layer, and so our very large number of neurons is going to explode the number of weights at the next layer. And this is where pooling can come to our rescue. Pooling is based on the idea that if our functions are learning to identify some local feature in the image, we might not need to know exactly which locations the feature happens in. It might be sufficient to figure out which broad areas of the image has the feature happened in order to do our subsequent calculations. And so we could take some, for example, 3 by 3 or 5 by 5 window from our hidden layer and somehow pool together the results of the neurons in that region. This pooling is generally not a learned function, but rather some really easy to compute way of aggregating the results, either by averaging them or by taking a max. A possible justification for pooling many neurons by a max is if we're thinking of those neurons as feature detectors, where they'll go off if the feature that they're looking for has happened, then taking a max over several nearby windows would tell us, did the feature detector go off in any of those windows? This is obviously an imperfect analogy because we don't know exactly what function the neurons are learning, but max pooling is very effective at reducing the dimensionality of the problem, and in practice often results in very effective deep learning. So let's suppose that after our convolutional layer, we added a 5x5 max pooling. Now our number of neurons is reduced by a factor of 5 on both the height and width dimensions. So after pooling, we have only 4,800 neurons, which is much less than our original 200 by 300 by 3 inputs in the image. And so adding another hidden layer after this one will no longer be a disaster. A useful exercise to think about would be if we added another convolutional layer after our max pooling, and you can take your pick of kernel size and strides, how many neurons and how many parameters would we end up with for that convolutional layer that is still doing two-dimensional convolution over the height and width of this tensor, but where each function that is applied to a given window will receive input from all 50 neurons across the depth dimension. I recommend trying to work this out with paper and pencil, and then check your work by creating such a network in your favorite library and having it print out the summary information for that model, which will tell you exactly how many neurons and how many parameters each layer has. The last thing to mention is that we've been considering two-dimensional convolution when we are thinking about sliding windows over a two-dimensional image, but it's entirely possible to do convolution on inputs with other dimensions. One-dimensional convolution would mean that we are sliding windows over an input vector, and so the nodes in the layer could be arranged much like we do for a dense network, but instead of connecting to everything, we would have neurons connected to only nearby inputs in the previous layer. One-dimensional convolution is great for time series data, and an example where that can come up is processing audio signals. Three-dimensional convolution comes up frequently in video processing, where we can think of the frames of a video as a third dimension, and we might want to not only slide our windows across the height and width of the image, but also through the time dimension represented by the video frames. These other sorts of variants may have their own hyperparameters, and there are other hyperparameters that you may see when using deep learning libraries. But I hope that this has given you enough of a conceptual introduction to 2D convolution and the parameters that you might care about to start applying it in your own projects.